Hello and welcome back. The new topic is the torsion stress. If we have tube which is fixed at the end and we have applied torsion T in the positive direction, when you apply the torsion in the anti-clockwise, this will be considered as in the positive direction, represented by the double-headed arrow. Due to the application of the torsion, there will be shear stresses. These shear stresses will vary based on the distance between center to the edge, and tau maximum, which is the shear stress due to torsion, will be maximum value when the radius becomes equal to C, when rho is equal to C, whereas rho is the radius of the circle from the center of the circle to any point. So tau, which is the general expression, will be equal to rho over C multiplied by tau maximum. Rho is the center line to the point you want to calculate the tau at, and C is the radius. Tau maximum is the maximum value. When the shaft is subjected to torsion, shear stress is developed and varies as a function of radial distance r. When r is equal to C, tau becoming tau max. Here there is a discussion, what about the positive and the negative direction of the torsion? If it is anti-clockwise, then it could be represented by double-headed arrow going out of the body, and from the other direction it would be coming out from the cylinder, while for the negative one it is rotating in the clockwise direction. It is pointing the double-headed arrow as if it is making compression to the cylinder, and the opposite side for balance, it will be also double-headed, will be directed to the cylinder. We have talked about the shear stress, but in the meantime we'll find that due to the torsion application, there will be change of the angle theta. This is associated with the longitudinal dimension of the shaft, and this angle of twist theta can be expressed as equal to the torsion multiplied by the length of the specimen divided by the polar moment of inertia divided by G, which is a modulus of rigidity, and the tau itself from the previous expression, that tau max will be equal to the torsion multiplied by the radius r divided by the polar moment of inertia. What about the values of the polar moment of inertia? If you have a solid cylindrical shaft of diameter d, then the polar moment of inertia will be equal to pi over 32 multiplied by the diameter to the power of 4, and the tau maximum in this case will be equal to 16 multiplied by the torsion value over pi d cube. And for the hollow cylindrical shaft, where there is a thickness and there is two diameters, inner diameter and outer diameter, so the polar will be the same expression, provided that inside the bracket is d4, capital D4 minus small d4, and the tau max will be 16t d divided by pi d to the 4 minus d to the 4. The small one is the inner diameter. This shaft sometimes is used for power transmission, and the power zeta transmitted by the torque T rotating at the angular speed omega is given by zeta equal to T by omega, where the omega is measured in radians per unit time. If the shaft is rotating with a frequency of f revolution per unit time, then omega will be equal to 2 pi frequency, which gives that zeta is equal to T multiplied by 2 by f. This is the expression for the omega. We substitute it here, and therefore the torque can be expressed as T equal to zeta divided by 2 by f. And this is the same torque which is causing shear stress of the cylinder. In SI units, the zeta is usually measured in watt, and 1 watt is equal to 1 Newton dot meter per second, and if it is in hertz, and 1 hertz is equal to 1 rotation per second. In US customer units, zeta is in pound inch per second, and F in hertz, and the torque would be in pound inch. We come to example number 7. Steel shaft 3 feet long, has a diameter of 4 inches, subjected to torque of 15 kb/foot. Determine the maximum shearing stress and the angle of twist using modulus of rigidity equal to 12 by 10 to the power of 6 pound per square inch. We'll continue next time. Thanks a lot and see you.